All right. So, as interesting as cheese is, maybe it's time to discuss some algebraic geometry instead. All right. So, first of all, are there any questions lingering in people's minds? I unfortunately didn't write it down, so I've actually lost track of what day I told you to tell me what your presentation topic is, but probably that's now, roughly, something like that. So please, if you haven't told me, I think probably most of you here have told me, but just encouraging you to think about that. All right, great. Anything else? Okay. So we talked last time about how line bundles are related to projective space. So if I want to map from my scheme to projective space, then that's equivalent to having a line bundle and n+1 sections of that line bundle. And I want to emphasize, I realized I didn't say this in quite the way that Raquel does. He says, oh, it's this data up to isomorphism. But what's an isomorphism of this data? It's an isomorphism of L to another line bundle, L prime, that sends these guys to your other sections. And in particular, you might ask, well, wait, how unique, if I fix the L, how unique are these sections? And the answer is that it's up to multiplication by a global invertible function, because that's what gives you an automorphism of this line bundle. I look at from any line bundle to itself, that's always the global invertible functions. Right? Because locally, this is isomorphic to the structure sheaf. The automorphisms of the structure sheaf as an O of X module are multiplication by invertible functions. And that sort of gluing those automorphisms gluing together is just saying that this is a section over the whole scheme of global invertible functions. Yes. Well, it's the same thing. You can. I mean, this is as O of X modules. Oh, sorry. Yeah, I see what you're saying. You're right. Sorry. Yeah, and what I'm looking for here is isomorphisms. Right. So yes, you're right. You should have that was a mistake on my part. If I wanted endomorphisms, I would just have functions. I wouldn't have the invertibility restriction. Yes, thanks for catching it. Okay, cool. So the obvious question here is, how do I come up with line bundles? How do I think about what the set of line bundles is? And then I can worry about choosing these sections later. So sort of a very important question. And one helpful way to think about it is the isomorphism classes of line bundles. Line bundles form a group. This group is called the Picard group, generally denoted pic of X. This is a really, really important invariant of the scheme X. And the multiplication in this group is tensor product of line bundles. I'll mention here, right, if you've encountered the pick in the context of pick of a ring, that's pick of spec of that ring as a scheme. Right, so pick of a ring is defined using invertible modules. And that's exactly the same as invertible sheaves if the scheme is alpha. Okay, great. So a natural question is, given a scheme, how do I calculate what this Picard group is? And it turns out there is a really useful way to do this. I mean, obviously it's still challenging, but there's a sort of concrete way to think about it. Just to make my life easier, throughout, I'm going to be assuming that x is integral and normal. The integral part is really just for convenience. You can figure out relatively easily how to extend the non-integral case. Normal, I don't know, it's maybe a little more important. And you'll see why in a moment. Yeah. Those line bundles. So, right, in this case, yeah. I mean, there's also a sheaf, an endomorphism sheaf, which is the structure sheaf. And similarly, there's an automorphism sheaf, which is the invertible elements of the structure sheaf. Right? But when you want to find, when this is interpreted in the category of O of X sheaves, or in the category of coherent sheaves, whatever you want, right? So from there to there, it's by taking global sections, right? So if I had looked at the automorphism sheaf, then I would get the sheaf of invertible functions. All right. Any other questions? All right. So the integrality is really for convenience. The normality, I mean, also for convenience. So somehow this wouldn't be that seriously different if you were normal, but you might have to do some hemming and hawing. So the trick we want to do here is, instead of trying to classify line bundles right away, let's classify line bundles with a section. And I'm going to even say with a choice of rational section. I will allow my section to only be defined on an open subset. So it has some like holes somewhere. Yes. Yes. We defined how to tensor locally free sheaves, and line bundles are locally free sheaves. I mean, if you think about this in terms of transition functions, it's multiply the transition functions. All right, and we'll see in a moment how to sort of interpret it in this world. All right. So we classify line bundles with a choice of rational sections, L. And what we can do with a line bundle and a choice of rational section is we can look at where that section has zeros and poles. So the reason I put normal here is then it's easier to kind of talk about what that means, and in particular to talk about the multiplicity of a zero or a pole. So by Kroll, S vanishes. Ooh, I should specify here, S is not zero. So in that case, Kroll's principal ideal theorem tells me that S vanishes on a finite union of codimension 1 subschemes, which I might as well assume are reduced. Right? So this is a statement that I only have to prove locally after intersection with an affine open. I can assume that my line bundle is trivial on that affine open. So I might as well think of S as just a function. And then this is exactly what Kroll's principal ideal theorem tells me, codimension 1. So that's the important part, that it's all things of codimension 1. Okay. But there's an extra piece of data I want, right? If I took S and I squared it, which you might say, wait a second, you can't multiply a section of a line bundle by a section of a line bundle, but of course you can, but you get a section of the tensor product. So for example, I could look at the tensor square of L and S squared, and of course that would vanish at exactly the same spots. So I need some extra information that distinguishes between these two guys. And I would say, oh, well, this guy's different. It vanishes to twice the order at every place where it vanishes. And of course, I should have said vanishes and poles, right? Since it's a rational section, it's allowed to have poles. All right. So what do I mean by multiplicity, right? That it vanishes to such and such an order or has a pole to such and such an order. I go back and I say, there's a hint here in the fact that I assumed that things are normal. So let y1 up through yk be irreducible components. Zeros and poles. Well, then I can look at the generic point of each of these components. I'll let eta 1 up through eta k be their generic points. So I can look at the local ring at these generic points. I look at this local ring, should have written X here. And the fact that these are codimension 1 and X is normal tells me these have a special structure. They're DVRs. So each of these guys, I have my maximal ideal. Okay. And that's generated by a single element TK. This guy's, I'll remind you, is called a uniformizer. And what this guy does is he defines what it means to vanish to order 1 on this subscheme. Tells me that if I take this guy and I multiply him by something invertible in this local ring, I'll get something that vanishes to order 1. And if I take t to the k and raise it to the mth power, whatever m is, then I'll get something that vanishes to order m. Or if m is negative, I get something with a pole whose order is minus m. So if I take this local ring and I take its unit group and I multiply that by tk m, that equals either 0 of order m or a whole order minus m. All right, and I had mentioned, right, the V here stands for valuation, and the valuation is the function that takes a non-zero element of this ring and spits out what power of t it's a unit. So if I look, there's a function val y I, or I guess I've been using one. Oh, right, I used k here as the dummy variable and the number of these is bad. Okay, so if I have a valuation for y of k, which just means when I apply this to some unit times key k to the m, it spits out m. So this is the function that vanishes to what degree I vanish or have a pole along this codimension 1. And this only makes sense because this is a regular local ring. So this guy being a DVR tells me sort of generically transversely to y of k, I get something nice and smooth. And it makes sense to ask what order do I vanish to generically in y of k. All right, I can say this kind of more invariantly by saying that val y of k of s is equal to m, where s times O of yk times s. So that's a bunch of sections of the line bundle. And that should be equal to y theta k to the m times the stalk of the line bundle. Like, yeah. What is this? A unit. Right. So the thing I'm using here is if I'm a unit in this local ring, obviously I don't vanish. That's like what it means to not vanish at a point. So I'm measuring how far from being a unit am, right? And in a general crazy local ring, there are kind of lots of different directions in which you could differ from being a unit, right? If you look at the local ring of A2 at a point, there's like vanishing along the x-axis, there's vanishing along the y-axis, there's vanishing along all these other one-dimensional subschemes. And so that's kind of a complicated thing. But because this guy is codimension 1, the local ring is really simple. There's a bunch of invertible stuff, and then there's one guy that generates the maximal ideal. And so I can see to what degree I vanish by just saying what power of that guy am. And I mean, I should say, this sort of coincides with the usual notions of vanishing to such and such an order, which are common in analysis. Right? So it sort of behaves the same way as those notions. All right. So what this means is I can take my line bundle and my rational section, and I can look at the corresponding information of these subvarieties and the orders of vanishing poles up. What sort of thing is that? It's what's called a Weil divisor. So this is most often what people mean by divisor, but there are other competing notions of divisor, which can be important. So this is a formal sum integral subschemes of codimension 1 with integer coefficients. So if I look at div of S, that means I take the sum over these y k's of the valuation on yk of S. So I look generically to what order does S vanish or have a pole on yks. I multiply that by the formal symbol for y of k. All right. So the they divisors form a group. It's just the free abelian group generated by these formal symbols for integral subschemes. We'll call this they of X. All right. The divisors of this form a subgroup. There are divisors, if you're which can't be written this way because something that's written this way, it has to correspond to a locally principal subscheme. You have to be able to locally write your subscheme as the vanishing set locus of one thing, and you can't always do that. So inside here, there's a set of locally principal divisors. But this is the divisor of the form. S section of a line bundle. Sorry, I shouldn't write this. Because it's not just a section, a rational section. A line bundle. Yeah. Oh, yeah, sorry, I should have written eta k. Yeah, this is all happening at the generic point of the, yeah. You don't want to do that because it's not, well, I mean, you can do whatever you want to do, but that's not quite the right way to think about it, I think. You want to sort of remember that maybe these YKs kind of have different sizes. Well, so for example, they might have different homology classes, right? A natural way to sort of think about this, one natural invariant of this would be this guy has a homology class assigned to it, and I take the sum with these coefficients, right? I think that might kind of be what you were trying to get at. but the YK doesn't necessarily. And we'll get to some examples, and then I think it will be sort of clear what kind of issue I'm talking about. But let's talk about this sort of abstract story a tiny bit longer. So one question you might ask is, how good of an invariant is div S? How much does this tell us about S and about L? The answer is everything. So if I get the same divisor twice, or S a section of L, S prime a section of L prime, then there's an isomorphism from L to L prime that sends S to S prime. And the proof is actually really easy. The proof is, look at the ratio. This ratio, it has no zeros and poles, because S and S prime, they vanish to the same order everywhere. They have poles to the same order everywhere. So, I should have done it in the opposite order. Multiplication by this guy gives me an isomorphism between these line bundles. Because whenever I restrict to small enough open sets where these guys trivialize, this becomes an invertible function. Okay, so that's pretty good, right? This tells us that we can always construct line bundles by looking at locally principal divisors and saying, oh, well, any section that this is the divisor of will give me my line bundle. Let's try to do a little bit better. So if what I wanted was just the underlying line bundle, I would think about, well, how unique is S? So if lambda has two rational sections, S and S prime, what's the relationship between S and S prime? In particular, what's the relationship between their divisors? Well, in this case, S prime over S, this is now a rational function, an element of K of X. So what this is telling me, you can check, if I take the divisor of this rational function, that's the divisor of the difference between the divisors for these guys, right? This is just because your level of zero and pole adds when you multiply two things. Right? So locally, I can still think about these guys as functions. And I just use the fact that when I have two functions and I take the ratio between them, the level of the order of vanishing or the order pole, I just take the difference. So I can also define in here a subgroup of principal divisors. So this is the things of the form div of f for f a rational function. All right, and so what have I found here? I found for every line bundle, it has some rational section. And so because I can trivialize it in an open set and use a function in that open set, so it must be represented by a class in locally principal divisors. And how unique is that class? Well, exactly up to addition of truly principal divisors, which correspond to the trivial bundle. So what this is telling me is theorem, I have a map from locally principal divisors to pick, which is take my locally principal divisor, find an L and an S that realize that divisor, and just remember what L is. And that becomes an isomorphism if I take the quotient by principal divisors. All right, so this tells me how to find all line bundles. Maybe not that explicit, because you have to figure out what all the locally principal divisors are, but it tells you something. And maybe one more. If X is smooth, or more generally, factorial. So factorial, this is almost by definition, factorial says that these local rings are UFDs. In a UFD, every codimension one irreducible subscheme is principal. So if I'm factorial, then every Ve divisor is locally principal. Okay, and in that case, pick of X is exactly all Ve divisors divided by the principal Ve divisors. Okay, so let's talk about an example, because this is getting kind of big and abstract. What happens if I take X equals Pn? I know that I have a bunch, so inside here, if I have an irreducible codimension one subscheme, then that's equal to V of F for F a homogeneous polynomial. All right, so that means that if I have some Ve divisor, Pn is smooth, so I don't have to worry about whether something is locally principal. Everything's going to be locally principal. If I have some Ve divisor, some AI yi, right, then I can write these yi's as V of Fi. And then this is going to be the divisor of, take the product of the Fi's raised to the AI's. Since these are all different, or I can assume I don't repeat any yi's, I don't repeat any Fi's. All the Fi's are co-primed to each other. And so I can prove this carefully by thinking about the local ring where I localize the maximal ideal, not maximal, the prime ideal generated by each Fi, and all the other Fj's are units in that localization. So I just ignore them. All right. Well, I found a rational section of a line bundle that this is the divisor of. What line bundle is this a rational section of? This is a rational section of O of some AI times degree of fi. So we see sort of the first example of this thing I was mentioning, that you want to somehow, think about these yi's as not being consistently all the same size. So I mean, in this case, it really is H2. Like each of these subschemes by Poincare duality defines me a class in the second cohomology of Pn, and there's an isomorphism of that second cohomology to the integers, which exactly sends one of the class of one of these guys to the degree of f. And so I'm just seeing what cohomology class I get in here. The magic word here is churn class. The churn class of this line bundle is the sum of those classes in H2. But that's getting outside the scope of this course. But you should think of this as being sort of some information which includes homology classes, but also includes more algebraic stuff. So the homology is part of it, but it's not the only thing, except in P. Okay, so this proves theorem, any line bundle on Pn is isomorphic to OK for some k. Because if I had some other line bundle, I could take a rational section of it, I would get some divisor, I would do this process, and then I would say, oh shoot, I proved that line bundle was isomorphic to O of k, where k is determined by this weighted sum of degrees. Okay, surviving. All right, any questions? So there, oh, yes. Yeah, it's complex codimension 1, right? So it's real codimension 2. Yeah, right. The first churn class is always in H2. Right? So it really is, if you think about this line bundle as an honest complex line bundle, in the smooth category, then the churn class that you get by like integrating the curvature is still telling you what this sum of degrees is, telling you what line bundle you are. But there are other situations where it loses information. So maybe I should mention, we had talked previously about this guy. Let me projectivize this. So we looked at the vanishing set of this inside P2. This is a smooth elliptic curve. So what happens if we take line bundles on this guy? We'll sort of try to come back to this later. But if I look at pick of this guy, so let's call this C, well, I get a factor, which is Z, which sort of has this same flavor of what's a divisor in here? It's a finite weighted sum of points. This is smooth in dimension 1. So in this case, a divisor equals a sum of points. And it turns out, well, there's a Z that measures how many points are there up to sign. But then there's an extra component, which is actually in bijection with the curve itself. And this is the additive structure on the elliptic curve. So this satisfies the property of if I take a sum of the AYs, AI, and now I'm going to be taking particular points, this ends up being equal to sum of the AIs times the base point for my elliptic curve operation, which I can choose arbitrarily. -1, plus I take the sum of all the PIs in the elliptic curve addition. So in particular, the way people will often write this is if I look at P minus O minus the base point, and I add two of these, then this becomes the elliptic curve addition of P and Q minus O. And this is really sort of the right way to define the elliptic curve addition. That when I take these two classes and I add them together, I get something else of degree 0. And by identifying the curve with this guy. I should mention in 446, we actually did talk about this. We talked about the class group of C minus the point at infinity, and then we just got the curve, not the factor of Z. All right. So some additional points which are important. So you can think more systematically about how to reconstruct the line bundle from the divisor by defining a quasi-coherent sheaf O of D. So this is the quasi-coherent sheaf defined by, I'm still assuming that X is integral and normal. For simplicity. So when I look at the sections of this on an open set, then this is equal to the F in K of X, such that for all Y contained in my open set, codimension 1, I have that the valuation along Y of F plus AY, where here I have some divisor D, which is some formal sum, where all but finitely many of these AY are 0, is positive. So what this is saying here is my AY sort of gives me a shift in my definition of whether I'm getting a 0 or a pole along the divisor. So I sort of am looking for sections of this line bundle in the same way that I would think of looking for global functions by making sure that they don't have any poles on one-dimensional codimension 1 subschemes. But now what I'm doing is I'm sort of starting with a section that I fixed the zeros and poles of, and I'm seeing if multiplying by a rational function cancels those poles. So what this is saying is 1 as a rational section as div 1 equals D. So even though the sections of this I'm identifying with rational functions, sort of really what I'm identifying them with is the rational functions times a formal guy S, whose poles and zeros I've fixed. But I can tell whether that guy times a rational function defines a nice section by just checking, does it have poles and zeros in the right places? Yeah. Mhm. Yes. It's not necessarily locally free. Right. So theorem, if D is locally principal, then O of D is a line bundle. I mean, there might also be cases where it's a line bundle, but it's the line bundle for a different divisor. But certainly, if you look at the theorem, it doesn't say that this is locally free for all V divisors. It says it's locally free for locally principal ones. All right. So we're pretty much out of time. Let me mention a few things here, though. So what this is telling us, which we'll kind of expand on later, is that you can sort of try to understand maps to projective space by fixing this divisor first. What does the divisor mean in terms of maps to projective space? So if I have my X and I'm mapping this to projective space, I have my X0 up through Xn on projective space, and I have my S0 and Sn, which are determining this map. So how do I think about the divisor of Si? It's the pre-image, the pullback of the divisor of Xi, which is just a hyperplane. So if I think about, like if I try to fix these functions Si by choosing their divisors first, what am I doing? I'm trying to construct a map to Pn by telling you what the pre-image of a hyperplane is going to be. And I can't always make that work because maybe the associated line bundle doesn't have enough sections. But for example, right, we had talked about this Segre embedding, where I take Pn times Pm going into P plus 1 minus 1. And exactly what I'm doing here is I'm saying, if I take a hyperplane in here and a hyperplane in here, then H times Pm union Pn times H prime should be the pre-image of a hyperplane. And one of the kind of cool things about this story is, right, once I choose what I want the pre-image of a hyperplane to be, there's sort of a canonical way to try to construct a map to Pn where that happens, which is take the line bundle and take all of its sections, take the complete linear system. And that gives you kind of the best chance of having a map where this is the pre-image of a hyperplane. Well, I guess I'm out of time, so I'll just stop here.